Hey, welcome back. In this video, we're going to discuss a very useful method. This method is used in both programming and in combinatorics. It's called decrease and conquer. But before we talk about decrease and conquer, we're going to talk about a more well-known method called divide and conquer. So divide and conquer and decrease and conquer are a lot alike. They're both programming methods. And in divide and conquer, the idea is that if we're given a problem, we break it down into two or more subproblems. So in particular, two or more, not one. It has to be at least two subproblems. And we do this recursively until the subproblems become easy to solve. And one example of this is merge sort, which you probably have seen before if you are a computer science major or if you've taken some computer science courses. So in merge sort, you are given some list of elements and you want to sort them into the correct order. And if you have some list and it has n elements, then starting with that list, what you can do is split it into two sublists, each of size approximately half the size of your original list. And then you can sort each of the sublists and merge them. And this part right here, when we say sort each of the sublists, that's recursive right there. So the way that we're sorting those sublists, it's the same thing that we do with the original list. We split them, each of them, into two smaller sublists, and then we sort those sublists and merge them. So here's an example. So let's consider a given list that is in the opposite order that we would want. So we have, let's say, an n equals 8 example. And our given list is this one. So that's the original. And first thing we can do here with merge sort, we can split it into two sublists. And we got to sort each of them and then merge them after we've sorted them. So for each of these sublists, we got to do the sort on them. So it's recursive. So it means we're going to have to split each of them into two sublists. So we got an 8, 7 here, a 6, 5 here. So it's convenient to draw this as a tree. I think it looks kind of nicer that way. And we can then do the same thing. So we have this row of the tree now with all of these sublists at depth 2. So our original list had length 8. The sublist at depth 1 had length 4. And now this depth 2 of the tree, the sublists here have length 2. So the length is going down by a power of 2 each time. And so we have to sort these sublists in this second row of the tree. So when I say second row, I'm saying like row 0 is here, row 1, and row 2. And so the very last row of the tree we're going to make, we're just going to apply our recursive function again. We got to split each of these sublists. We got to split them in half, just like all the other sublists. And so this is our very last row of the tree. And now we've hit the spot where the subproblems are easy to solve at this point. So subproblems are easy to solve. Why is that? Well, all of our sublists now at the bottom have length 1. So they are already sorted for us. So what we can do now is we can merge them. So we need to merge them up the tree. So the 8 and the 7, we merge them and we put them in the correct sorted order when we merge them. And that gives us a 7, 8 when we merge them in the correct sorted order. And we can do the same thing with each of these sublists in this row of our tree. So that row 2. So we merge the 6 and the 5 in the correct sorted order to give us a 5, 6. The 4 and the 3, when we merge them in the correct sorted order, we get 3, 4. And then the 2 and the 1, when we merge them in the correct sorted order, we get 1, 2. Okay, and then we have this row complete, and now we need to go up to the next row. So I will be erasing that next row. And now we have the 7, 8, the 5, and 6, and we have to merge them in the correct sorted order. So that gives us 5, 6, 7, 8. And the 3, 4, and the 1, 2, we have to merge them in the correct sorted order. That gives us 1, 2, 3, 4. And then finally, the very top row, we have 5, 6, 7, 8, and 1, 2, 3, 4. And we got to merge them in the correct sorted order. And that gives us 1, 2, 3, 4, 5, 6, 7, 8. So this is an example of a divide and conquer, because our original problem here, we just kept on splitting it into subproblems until they became easy to solve. And they were easy to solve down here because when you have only one element on your list, it's already sorted no matter what. So in addition to merge sort, there's another really interesting example of a divide and conquer algorithm. So it's related to something that we use pretty often, something we usually do with a calculator, I guess, but back in elementary and middle school, we had to do a lot of it by hand, and it is multiplication. So suppose you're given two n-digit numbers. Let's say two pretty nice ones like 1, 1, 1, and 1, 1, 1. And I claim when we use standard multiplication, it requires n squared single digit products. So n squared here is n times n. So we have two n-digit numbers. So why would that be? Well, when we're multiplying these two, these are each 3 digits. So we multiply those, and those, these 3, and these 3. So it's 3 times 3, so 9, which is 3 squared. And that's n equals 3. And those multiplications, all we have to do is just do each of those single digit products and then throw some zeros on the end. So we have a 1, and then we threw a 0 on. We have a 1. Each of these ones, we're just getting from 1 times a 1. And then the next row, we have a 1, we put an extra 0 on. We get a 1, we have to add extra 2 zeros, and then a 1 with an extra 3 zeros. So it's just our single digit products, 1 times 1, and we're just putting extra zeros on depending on the locations of the ones in these numbers. And then of course the last one, 100, 1000, and 10,000. So all of these are just ones with some extra zeros on. And if these were any other numbers, it would just be the products of the single digits with some extra zeros on. And then we just add all these up. So we get 1, 2, 3, 2, 1 for at least that product. And in general, we can use this method for any two n-digit numbers. We can just take their single digit products, put the necessary number of zeros in each one, and then add it up. That's basically what we're doing with the standard multiplication algorithm. And as you can see, the number of products we found was n squared. So this bullet makes sense. And there's this algorithm which allows you to do standard multiplication using approximately n to the 1.58 single digit products. We're not going to go into the details of it, but it is a example of divide and conquer. And one other thing that I want to mention about divide and conquer is that you can think about it like a strong induction proof. So with both of them, strong induction and divide and conquer, we're breaking down each problem into 2 or more subproblems. And then with the strong induction, we're doing this recursively until the subproblems are base cases. And with the divide and conquer, we do this recursively until the subproblems are easy to solve. So base cases, of course, are easy to solve. So base cases is just a specific case of an easy to solve problem. And we can think of some specific examples in which the strong induction proofs, they are really like a divide and conquer. So for example, that candy bar problem where we had a candy bar with n unit pieces and you're only allowed to make breaks between the pieces. And we said that the candy bar with n pieces requires n minus 1 breaks in order to break it into all only unit pieces. So when we proved that, we used strong induction, and that strong induction proof, it required us to use all of the previous cases. So we didn't know exactly where our first break occurred. So any of the previous cases, smaller lengths of the candy bar, were required for the proof. And that is very similar to a divide and conquer, because the idea there was we had this candy bar and we split it anywhere along the candy bar to get it into smaller pieces. And then each of these pieces, we would be doing splits on them as well in order to get them into unit pieces. So it's possible that the number of rows of this tree that we construct, it could have multiple different values for the total number of rows, depending on where we make these breaks. So as you see, it's a similar idea. We can use this tree idea to break down this problem, the candy bar problem, the same way we were breaking down the divide and conquer problem with the merge sort on the last slide. Another one that was a strong induction proof that is a very similar idea to the divide and conquer was proving that every integer greater than 1 is a prime or a product of primes. So when we had some integer n, which was not a prime, so we could write it as n equals a times b, where a and b were not equal to 1. Then we took the a and the b and we broke them down. And then we can say a equals xy if a is not prime, and b, this one, equals some m times n if b is not prime. So as you see, we can just keep on doing the tree with this one too. So the methods that we're using for these strong inductions, they are kind of parallel to the divide and conquer method that we were using on that previous slide. So divide and conquer and strong induction, they're very similar to each other. And one other type of proof that I'll mention that we've seen before, which is similar to divide and conquer, is solving linear recurrences. So when we solve linear recurrences, we take whatever our current case is. So if we're trying to prove, let's say, like a of k plus 1 equals n times 2 to the n, not n. So let's say k times 2 to the k. And we have some recurrence for this. So our recurrence, it could satisfy, for example, a sub k plus 2 equals, let's say, 4 a sub k plus 1 minus 4 a sub k. So some recurrence like this right here. And if we need to show that this was the solution to it, so we didn't specify the initial conditions, but we could say something like a sub 1 equals 0, a sub 2 equals 2. And then we could see from the recurrence right here, a sub 3, using that recurrence with the a sub 1 and a sub 2, we would get 8 from that. And that looks good so far. So everything with that looks correct so far. But if we wanted to prove that this held in general, we would take that a sub k plus 2, and we know that's equal to 4 a sub k plus 1 minus 4 a sub k. So if we're trying to prove that its value is the k times 2 to the k, then we're just using the values for the previous ones. So a sub k plus 1, a sub k, and we can get their values from a sub k for the a sub k plus 1 and a sub k minus 1. And for the a sub k, we got a sub k minus 1 and a sub k minus 2. So as you can see here, we have all these different trees, but all of them we can turn into trees like this. And this idea of turning into trees where the successive levels of our trees are smaller and smaller subproblems. This is the idea of divide and conquer. So now that we've seen a bunch of examples of divide and conquer, I want to focus for the rest of this video on the main topic, which is decrease and conquer. And decrease and conquer, like I said before, it's very similar to divide and conquer, except one key difference. Instead of having 2 or more subproblems in each step, we only have a single subproblem. And there are plenty of famous examples of decrease and conquer proofs. So one of them you might have seen before is binary search. And another one that you might have seen before is the Euclidean algorithm. We'll talk about both of them. So let's start with the binary search. But before we talk about it, let's also talk about the parallel with induction. So when we're doing decrease and conquer, it can be like weak induction. So when we were doing the divide and conquer, that was like strong induction. And the decrease and conquer, it can be like weak induction. That can happen. It doesn't necessarily have to be. So the reason for that is because when we reduce a problem to a smaller subproblem, the smaller subproblem does not have to be the preceding subproblem. It could be one before that. So we can say that decrease and conquer, it's like a strong induction where you only use one of the previously proved cases, but it does not necessarily have to be the last previously proved case. So it could be any of the previously proved cases, but just a single one. So now let's talk a little about binary search. So the idea of binary search is you're given some sorted list of elements, and you're given some other element, and we'll call it y. We'll say the elements in our list are the xi's, and we don't know if y is on the list or not, and we want to determine whether it's on the list, and if it is on the list, we want to figure out what is its index. So there's a method to do this, which is very fast. And we can describe this method in only a few steps. So given the sorted list, and the sorted list again, our elements are x0 up to x sub n minus 1. So 0 here, n minus 1 are endpoints. So we'll start out with L equals 0 and R equals n minus 1. This is for left and right. So we're making a window here. So we can think of, we have 0 here, we have n minus 1 here, and we'll start with the L and R here. And this is our list. It's some line that's representing our list of numbers. We want to figure out is a y on the list. Now, step 2, if L is greater than R, return not on list. So right now with L equals 0 and R equals n minus 1, we're assuming that n is at least 1 because our list is non-empty. So right now, L is not greater than R. So this step 2, it'll only happen if the L and R values get changed, and then our program sends us back to step 2. So in the beginning of the program, when we first run it, when we run step 1 and then we go to step 2 for the first time through step 2, nothing will happen because L and R start with L less than or equal to R. Now, step 3, assuming that we don't do step 2, or assuming that we do step 2, but nothing happens in step 2, then in step 3, we will let this variable m equal the floor function of L plus R over 2. So m is approximately in the middle of this interval between the left endpoint and the right endpoint. And I just want to emphasize that this middle, it is this is not, it's not going to be the x0 plus xn minus 1 over 2. So it's definitely not that. So here we are only talking about x sub m. So x sub m is not the same as x sub 0 plus x sub n minus 1 over 2. It could be the same as that, but it doesn't have to be. So once we've calculated this m value, we check a few cases. So in our list, this is a typo here. That a should be an x. Apologies. If x sub m is less than y, if x sub m is less than y, so we can look at our line here. So we got an x0 here, got an xn minus 1 over here, and an xm here. So if y is over here, then we want to move our left endpoint over here. So that's what we're going to do if y is over there. And in words, that means we'll let L equal m plus 1. And then we go back to step 2. So this is when step 2 can apply, when we can actually return a not on list, is when we go to step 4 and we change L, and then we go back to step 2. Step 5, this one is similar to step 4, except it's if xm is greater than y, that should also be an x. So if xm is greater than y, then in this case, we're talking about when y is over here, we want to move the r over in that case. And that means we want the r to be m minus 1. And again, we go back to step 2. And finally, the last case, if xm equals y, So in that case, that's a good case. That means that we found the element y. So in that case, we just return m. And that's it. So it's only these 6 steps. And we can do a pretty simple example here. So let's say we have a list of the first 11 primes. Okay, we'll say x0 here, x1, x2, x3, x4. Okay, there's our list. And let's say we haven't looked at that list for a while, and then someone gives us some number, this y value 23. We haven't seen that list in a long time. Can't remember if it's on there or not. And this list, we're going to do a binary search on it to figure out if it's on there. So we take x0, x10. So 10 is n minus 1. N minus 1 equals 10. And then we do step 1 of our algorithm. We let L equals 0, R equals n minus 1. So L equals 0, R equals 10 at the beginning. If L is greater than R, return not on list for step 2. Right now, L is not greater than R, so step 2, that doesn't even apply. Now, step 3, let M equal the floor of L plus R over 2. So M equals the floor function of 0 plus 10 over 2. And that's just 5. And we're going to look now at x sub 5. So x sub 5 equals 13. And I'll also draw my L and R down here too. I'll call them L1 and R1. So x sub 5 equals 13. Our y value is greater than that. So we can say x sub m is less than y. Case 4 applies here. So we're going to let L equal m plus 1. So L now equals 6. So we can say, here's our L2, and this is our R2. So now we have L equals 6 and still R equals 10. And we got to go back to step 2. Step 2, if L is greater than R, return not on list. Well, L is not greater than R, so we're fine. So we'll go to step 3. Let M equal floor function of L plus R over 2. So M here, floor function of 6 plus 10 over 2. That gives us 8. So that's our new M. We got M equals 8. And X sub M equals X sub 8, which is 23. And that's our Y. So we found it. So that's good. So we return. So our program gives the output. The output it gives is 8. So it tells us the index of Y on our list. So there's our Y. And that's it. So that's an example of when the number is on the list. And I'll let you think about what happens when the number is not on the list and why it terminates in that case. And here's a problem for you to think about. Explain why this algorithm, given this list of length n, takes big O of log n comparisons to find the position of y on the list or to determine that it's not on the list. So regardless of whether or not y is on the list, prove that there exists some constant c such that the number of comparisons has an upper bound of c log n for all n. And you can also prove that there exist constants c and d such that the number of comparisons is at most c log n for all n at least d. That's fine too. So either of those, you can prove that, and that will give, by definition, that will show that the number of comparisons is big O of log n. Let's also look at another example of a decrease and conquer algorithm. This one, Euclidean algorithm, you might have seen before when you learn about the greatest common divisor. So the greatest common divisor, just to review, of two integers a and b, which we'll assume are positive, it is the greatest positive integer c that divides both a and b. And the Euclidean algorithm gives us a method for finding the greatest common divisor mechanically. So here's how we can do it. Suppose that between the two numbers, a is greater than b. Now, the reason why we can assume this is if a equals b, then the GCD of a and b is equal to a, which equals b. So the GCD is immediate in that case. We could assume that a is greater than or equal to b. It doesn't even matter. So having it be greater than b, having b greater than or equal to b, it's not going to make any difference here because, again, this case is immediate. Now, here is the substance of the Euclidean algorithm, the crucial step. So we take the remainder when you divide a by b. So if a is divisible by b, then when we take the remainder, it's going to be a zero remainder. And we can write it when we take the remainder, we can say a equals b q plus r. So that r, we have r is between 0 and it has to be less than b. And all of these are integers here. And that q is our quotient. So it's like how we did division back in elementary school. So there's our bound on r. And like I said, if there's no remainder, if a is a multiple of b, then our remainder will be 0. And in that case, if there is no remainder, we can say that the greatest common divisor of a and b, assuming that a is at least b, which we have assumed in this top step, the greatest common divisor when r equals 0 is just going to be b, because b is less than or equal to a, and a divided by b has remainder 0. So in that case, getting the GCD is pretty easy. In other cases, we can just reduce our problem. So we're taking this problem, this GCD problem for a and b, and we're reducing it to a smaller subproblem. And what we're reducing it to here is BR. So we're making the A smaller because we're assuming that we're definitely making the A smaller, because the only way that we wouldn't be making the A smaller would be if A equaled B. But if A equaled B, then we would have gotten finished in this step because the R would have been 0. So if we manage to get to step 4, then A didn't equal B. So in this case, the B is going to be less than A, and the R is going to be less than B. That is by definition of remainder. So this is a strictly smaller subproblem in both of these variables. And then we just go back to step 1 with the subproblem. And the claim is that the GCD of A and B is the same as the GCD of B and R. So we can just keep on going to smaller and smaller subproblems until it hits one that is really easy to solve. So the easiest one to solve is going to be when it terminates. It's going to terminate with a step 3. So at some point, A will be divisible by B. So this Euclidean algorithm, the reason why it works is because GCD of A and B equals GCD of B and R. And let's talk about for a little bit why that's true. So why does it work? So we can see this, we can suppose that C is any divisor of A and B. So if C divides both A and B, then we can say A equals JC, B equals KC for some J and K that are integers. And we'll also assume C is an integer, of course. And this means that R, which we know from over here, the R is equal to A minus BQ, which equals JC minus, we'll write it as KC times Q. We can write that as J minus KQ times C. So R is divisible by C. So C divides R and B. It still divides B because it divided B before. So any divisor of A and B, any divisor of A and B is a divisor of B and R. And if we have a divisor of B and R, so if we have some D that divides both B and R, then if B is a multiple of D and R is a multiple of D, then of course A must also be a multiple of D. So if this B right here is divisible by D, if D divides that B and D divides this R, then D has to divide that A, because A would be a multiple of D times Q plus another multiple of D, which is a multiple of D. So we can say, and vice versa. So any divisor of A and B is a divisor of B and R, and any divisor of B and R is a divisor of A and B. So in particular, the greatest common divisor of A and B is a divisor of B and R. And the greatest common divisor of B and R is a divisor of A and B. So they have to be the exact same greatest common divisor. And each of the steps, we get the exact same greatest common divisor. So the GCD up here equals the GCD here, which equals the GCD that we get on the next step. And it keeps on going. So we just keep on getting remainders, replacing the B. Or sorry, not replacing the B. The remainders replacing the A. The B is the one that stays. So we keep on repeating the step. We get the remainder, replace the A, until we hit a point when the B divides the A and we get a remainder of 0. And when you get a remainder of 0, the GCD is just the B. And so it'll be good to look at a pretty small example. So we'll do one. So here's a nice small example. So let's look at 120 and 75, let's say. That'll be our A and B. So we take the remainder when you divide 120 by 75. That's going to be a remainder of 45. We replace that in the place of the 120. So we get 75 and 45. Then we divide 75 by 45 and look at the remainder. We get 30, which replaces the 75. So we got 45 and 30. We do the same thing with the 45 and 30. We divide by the 30. We look at the remainder. We get 15. So we got 30 and 15. And now the 30 is divisible by the 15. So there's our GCD. And that 15, so GCD of 120 and 75 equals 15. So that's a nice small example of the Euclidean algorithm. And here's a problem for you to think about. For each n greater than or equal to 1, find the greatest common divisor of these two numbers, 16 to the n minus 1 and 16 to the n plus 14. That brings us to the end of this video. Thanks for watching.